Hello there. Thanks for joining us yet again. This is Space Nuts. My name is Andrew Dunkley. We're here to talk astronomy and space science. And on today's program, we're going to look at a tiny, weeny, itsy-bitsy Jupiter. Yes, it's not nearly as big as they thought it was. In fact, it could lose status as a consequence of this. Maybe not, but we'll talk about that. We're also going to look at a flipping interesting comet and solar gravitational lens focal points. Could we visit them, and what will that mean? We'll find out on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us again to talk about all of that stuff and probably a lot more is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Good to see you again.
Good to see you
always.
too.
Yep, as always.
Love the hoopy shirt.
Oh, yeah. Sorry. It's a very tatty old one, this shirt. I shouldn't be buttoning it up.
This one's not tatty, but it's white and it's got more food on it than I've ever put in my stomach. So
Has it got the Space Nuts logo on it?
hang on. I've got one here somewhere, a Space Nuts logo.
Oh, yeah.
No, I have. It's not on this shirt. It's on the other white shirt.
Right.
But, where did that logo go? I've lost my logo. Anyway, we'll find it another day.
Better than losing your mojo.
That's true too, yes, indeed. Let's begin because we've got a lot to talk about. This first story looks at Jupiter, the biggest planet in our solar system, until we find Planet 9. And this is a story that's suggesting that Jupiter's not quite as big as we thought it was.
Yeah, it's shrunk by, 8 kilometres at the equator and 24 kilometres at the poles. So what this is all about, and I should just give you the numbers. So the revised radius of Jupiter at its equator is 71,488 kilometres, which is actually, I think, 4 kilometres less than we thought before, which doubles up to 8 kilometres when you're talking about diameter. But its polar radius, which is 66,842, and those two numbers are quite different, which is why Jupiter's flattened but at its poles, just as Saturn is. But that's actually 24 kilometres less than the previous estimations. So for the diameter, so it's not a huge amount, but it's enough.
Not when you're talking about the size of the planet. That's
exactly that's what I mean. Yeah, 71,004. So it's 140,000 kilometres or thereabouts in diameter, which is 11 Earth diameters, which is what we always say. So why? Well, first of all, how have these measurements been made? And the answer is that the old measurements actually go back a long way. They come from the Voyager and Pioneer era of the exploration of the outer planets. And that goes back to the 70s and 80s.
Oh, it does.
So what led to the diameter or the size of Jupiter that we've been using since then is what's called a radio occultation. So the spacecraft is behind, as it passes behind Jupiter, its signals get refracted actually by the atmosphere of the planet, probably scattered as well. But you can time it very accurately. You can time when the spacecraft disappears behind the planet and you know its trajectory. You can then time when it reappears. And from that, you can calculate and knowing about Jupiter's motion and the spacecraft's motion, you can calculate what the diameter is. So those are the values that we've been using ever since.
I think I know where all of this went wrong. They didn't allow for it stopping for gas.
The planet or the spacecraft?
The spacecraft.
Well, it's a gas giant. That's right. The planet's a gas giant. So yes, that's a good point.
Yep.
Anyway, I'll let that one pass. So moving on.
Wasn't very good.
It was all right for the start of the show. They usually get better as we go along. It's the new measurements come, of course, from the spacecraft that is currently in orbit and working away very hard at Jupiter, in orbit around the planet, and that is Juno, NASA's Juno mission, which has been orbiting Jupiter since 2016 and doing pretty well. It's it's a decade since we've had Juno, which, gosh, time flies, doesn't it?
Sure does.
Anyway, so that's allowed much more accurate measurements because that Juno spacecraft, its orbit is very well understood. It's fairly close to Jupiter. But you might think, well, why are we so keen to know the diameter of the planet to such a high degree of accuracy? And the answer is to do with our model. Because it is. Yeah, that's right. It's to do with our modelling of the planet's interior. Because a small difference like that can make a big difference to what we imagine the interior of the planet is like. And remember, of course, everybody, that Jupiter, all we see is its cloud belts. When we look at the planet, we don't see any surface or any hint of a surface. So the internal structure of Jupiter is something we have to deduce from other measurements, and an accurate measurement of the diameter of the planet comes into that. So that's the reason. It also one of the other things that's of interest in Jupiter is the behavior of the atmosphere itself and the winds that blow in Jupiter's atmosphere. And that also needs an accurate understanding of the diameter of the planet.
Yeah, I was just looking at that diagram that shows the different potential diameter situations based on the behavior of the planet. And yeah, without wind, it loses another, 14 kilometres?
Yes, that's right. It does. If you imagine the winds aren't there, it does. It shrinks. And by 14 kilometers exactly. That's the radius, not the diameter. We have a tiny figure that looks minuscule compared with the diameter of the planet itself, but it is important in understanding the upper atmosphere. It's if there were no winds, then what we will be seeing will be 14 kilometres smaller.
I'm surprised that it's taken us a decade to figure it out. I mean, Juno's been there nearly 10 years.
Yeah, but maybe the accuracy that we're getting with this relies on many passages of Juno around Jupiter. Because you're always, the chord that of the Jupiter's disk that the planet that the spacecraft flies behind is different every time, and so you probably need to build up a statistically significant sample of entry and egress times when you're looking at the object disappearing behind the planet. Occultation is what we call it, and occultation is when one object hides another, and that's how you're measuring these diameters. So yeah, it's probably taken 10 years, partly to amass the data to give us this kind of level of accuracy.
So okay, how accurate do you think it is now compared to those early flybys with Voyager and Pioneer?
That's a really good question, actually. I haven't seen any error estimates on, and as you know, in physics and certainly in astronomy too, you always need a plus or minus an error estimate as to what the likelihood of your measurement being that number is, and I haven't seen it for these, so I don't know the answer to that, but my guess is that we're talking about in the region of a kilometre, which is pretty impressive for something that diameter and something that's that far away, 500 million kilometres away. Yep. So
does this mean that our estimations of other planets in the solar system are probably a bit off as well? When you consider that Neptune, for example, I think we've only visited once. Would that be right?
Yeah, that's right. So yes, I think you're right. You certainly the estimates of planets beyond Jupiter and Saturn in terms of their diameter and physical characteristics will have much bigger error limits on them, just because we can't make the measurements as accurately as you can when you've got a spacecraft in orbit around one of them.
Okay, so that's a work in progress. Whenever we go back, we might be able to fix that.
Yep.
But I don't know. Have they got any missions planned for Neptune and Uranus or anything?
There's always calls for them because they're such interesting worlds.
Yeah.
But I don't think. I mean, I think there are lots of proposals, but I don't think there's anything funded. Might be wrong about that.
Yeah.
Maybe our listeners can tell me if I'm wrong about that.
They may well, because a lot of we've got one fellow on Facebook who regularly researches some of the things we talk about, and he publishes his findings on the Facebook podcast group.
Good on him.
And I think it's great. I've read a few of his explanations, and they're very good. So we're probably going to get sacked, but it's.
Surprised them sectors already.
Well, they can afford us. That's why we're still here.
Well, that's true. Yes, that's true. Yeah. We're very true.
No, it's a really good discussion point. So it sort of keeps the momentum going when we discuss these things. So I'm sure he'll work on our tiny Jupiter story, which
good.
Yes, which you can read about at the dailygalaxy.com website, or you can read the paper at Nature Astronomy. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
That's agreement, is that? Jordy, for goodness sake, I'm really sorry. Okay. He gets very enthusiastic. Hang on a minute, Andrew.
Space Nuts.
I couldn't help but turn that into a link.
It's brilliant. I'll tell him.
Gosh, it's just too good. It's just too good. He was going off his nut that day, wasn't he?
He was. He was. He does. Yes, he's very highly strung. That dog.
Yes, he is. Well, that's how he greeted us when we visited you late last year. He came tearing down the stairs,
doing his rooster impersonation.
No one could ever rob you, Fred. No one.
That's the one good thing about it. Yes, that is the one good thing.
They don't have to be big, aggressive dogs. They just have to be loud.
Or even, a brush turkey going past the window in the middle of the night. That's enough as well.
Yes, that's all it takes sometimes. Now, let's move on to our next story. And this is a story that's got scientists really, well, the headline says scientists stunned. We're talking about a comet that has done something really, really unusual. We're talking about Comet 41P. What's it done this time? Because it keeps making the news, this one.
Yes, it does. Tuttle Jacobini Crescak is its full name. Comet better known as 41P. It's an object probably a kilometre across, a flying iceberg, basically like comets are. And it orbits the sun, I think, about every 5.5 years. So it's in what we would call a short period comet orbit. And it's when it passes near the sun, of course, it does what comets do. It outgasses, produces basically plumes of gas leaving its surface. It's usually water ice being converted directly to water vapor by the process known as sublimation. But what has been recorded in fact, in quite a while ago, actually, I think this was 8 years ago, by a NASA spacecraft, observations made by NASA's Swift spacecraft, measuring its rotation. And basically, over 60 days, what's that, sort of 9 weeks or something like that, it slowed down from rotating once every 20 hours to once every 53 hours. So that is it's almost a factor of 3 in the level of spin that this comet has got.
Yeah.
And there's a suggestion that maybe it's now rotating in the other direction from what it was before, that there's been some sort of reverse.
It hasn't slowed down to about 1/3. It's reversed. So it's slowed down 5 times. Because it's gone back the other way.
it could be, I mean, part of it could be due to how you measure the rotation, because it could be tumbling as well. So you might be seeing it going the other way around. But it does seem to be, I think you're right. I think what you've just said is correct, that it's a reversal, a genuine reversal of its rotation direction. Yes, it's got much more than a factor of 3. That's right.
That kills my theory, because my first thought was, well, this must just be an observational error. But an observational error wouldn't get it the wrong way around. Unless, of course, you're talking about the colour of the universe, but we won't go there. But
wasn't my fault.
What else could be causing this change of behaviour?
Well, I think if it was anything other than a comet, if it was an asteroid doing this, or a planetesimal, or a distant, one of the distant Kuiper Belt objects, or something like that, if it was any of those, we would be utterly gobsmacked, because there's no physical mechanism to do that other than an interaction with another body. If you had two bodies gravitating close together, it could have an effect on the rotation. Yeah. But in fact, more especially a collision, that would do it as well. But with a comet, you've got this process that it outgasses, what I was saying earlier. As it gets near the sun, basically the ices start to vaporize, and you get a thrust from the outgassing material, which is what we call a non-gravitational perturbation. It's when the outgassing material is acting like a rocket engine, and it's changing the dynamics of the object as it's orbiting the sun. And you can imagine that if there was a formation of ice on the surface of the comet that essentially tilted the blast of the escaping material as it sublimated, as the material, the water mostly, went straight from a solid to a gas. It's like having a sort of vernier thruster. It's like where you've got a thrust that is changing the rotation of a spacecraft, because it's not going. The line of the thrust is not going through the centre of gravity of the comet. If it's off the centre of gravity, then it's going to impart a rotation on it. And if it's strong enough, then it might be enough to slow it down and perhaps even reverse its rotation. So that's what the thinking is, but it's never been seen before.
No, well, like retro rockets.
Yeah, that's right. It's a retro rocket, but one that's not slowing it down in its orbit. It's changing its rotation because of the angle that the rocket, if you want to call it that, the rocket exhaust is coming out.
Now, at the moment, it's 774 million kilometres from Earth, 5.18 astronomical units. And as you mentioned, this unusual behaviour was checked back in 2017, and they've only just sort of put a paper together to try and explain it. It's got a 5.4-year orbit, so it comes back quite often.
Yeah, that's right. It's basically captured by Jupiter, so its orbit is dictated. It would have been, in its early history, it would have been a comet coming into the inner solar system from the Oort cloud, this spherical sort of reservoir of comets, but would have had its orbit modified maybe several times by the influence of Jupiter, which is why it's now in this really short period orbit, 5.4 years. Yeah. There has been a suggestion that if you've got these sort of oblique outgassing that we've just been talking about that would change the rotation of the object, that might also signal that there might be weaknesses in the comet structure, and it may even be a precursor to it breaking up, which is something that I think will be observed with great interest as to how it progresses since this change of spin.
Yeah, maybe, and we could find out as late as or as soon as late 2028. I think is its next appearance near the sun or near us or whatever you like. So. We'll keep an eye on 41P, I guess.
41P, that's right. There was a proposal long ago to send a spacecraft to it. because it's a short period comet, so it's always in the inner solar system. And that was what was then called ESRO, the European Space Research Organisation, the precursor of ESA, the European Space Agency. And this is in the 1960s. They looked at sending a probe to that comet, but they changed their mind, so it never went.
Oh,
yeah, it's a pity, isn't it?
I'm sure that happens a lot in astronomy.
Yes.
I mean, not an easy thing to do to set up a mission and actually execute it. And you've got to come up with the dollars, and it's only so many 10-cent pieces can fit on a jar on the mantelpiece. So
Yeah. That's right.
yeah, all right. You can read all about Comet 41P at it's at the dailygalaxy.com website, but you can also read the paper. I think it's just been pre-published or there's a preprint available on the archive. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Space Nuts.
Now, Fred, to our final story on this episode, we've talked many times about gravitational lensing and some of the strange things that it does. You can watch something happen 2, 3, 4 times over the course of many years because of gravitational lensing, because the light is redirected and takes longer to get here. And so you can see something and go, oh, what was that? Hang on, I'll know again in a couple of years because, yeah, not quite. But what we're talking about what we're talking about in this particular case, though, is actually going out to a solar gravitational lens focal point. Is that the crux of the story?
It is, that's right. This is a really interesting kind of essay, really, on the Universe Today website by Andy Thomaswick about the solar gravitational lens and about how you'd get there. But the solar gravitational lens itself is really interesting. So the idea is, exactly as you've said, if you've got an object of any mass, and it happens with planets as well as stars, it's going to bend the light passing around it because it's distorting space under the protocols introduced by as we understand it, by the protocols introduced by Einstein's general theory of relativity. That's what lets us do all the calculations about this sort of thing. So you've got an object in space, it's bending the light around it, which means it acts kind of like a lens. It's a very odd sort of lens, though. I've seen a glass kind of interpretation of a gravitational lens. There's a specialist who works on this stuff in Melbourne who showed me her glass version of a gravitational lens. And it resembles, you know, the bottom of a wine glass where the stalk comes up out of the middle of that.
I know them
glass.
very well, Fred.
Yeah. Well, if you break the wine glass off and you're left with that sort of flared part at the bottom, that's more or less the same as a gravitational lens in the way it would act on the light going around it.
Okay.
So it's not like a magnifying glass, which is what you'd like it to be. It's this very peculiar cusp-shaped lens. And so it gives you a focus that is blurred, but it's because you know the properties of the object that's doing the lensing, and in this case we're talking about the sun. Because you know the properties of the sun, you can calculate what that blurring does to the image, and you can essentially compensate it. So you could recreate the light coming from a very distant object and recreate the image that the sun is forming as though it was a proper lens rather than a peculiar cusped lens. And that's what's sort of being proposed. Could we send a spacecraft to the solar gravitational lens focus where you could look directly back at a planet on the other side of the sun around a distant star? So you're looking into another solar system a long way away, but you're using the sun's gravity to bend that light by relativity and focus it to a point. And if you put a spacecraft there with a camera and a fancy computer, you might be able to reveal continents on an exoplanet, for example, or even cities. That's the sort of thing that people are thinking of. So here's the snag, though. It's a great idea, but the snag is...
I think I just read that exact paragraph as you were about to say it, so I might blow the whistle.
Yeah, well, you can.
No, you do it.
It's the distance, isn't it? It's about somewhere between 650 and 900 astronomical units is what's quoted in this article. Yep. And an astronomical unit is 150 million kilometers. So it is a number with a lot of zeros after it in kilometers. And, you know, it's getting your spacecraft there that is the issue. We're talking about, well, the estimate here is 4 times further than Voyager 1 has travelled, and that, as we know, is 23 light hours away. They reckon that it would be more than another 130 years for Voyager 1 to get to the sun's gravitational lens point.
By my calculation, and this is probably way wrong, 97,500 million kilometres.
Sounds about right.
Yeah.
Sounds like a lot. Yep.
I didn't think my calculator could fit that many numbers on it. Remember the old calculators when they first came out? If you gave it too big a problem, it would just give you a little E.
Yeah.
E for error.
Right.
No, I can't do that. Sorry.
Yep. This computer says no, really, isn't it?
That's right. Yeah, that's a long way away and very difficult to achieve. But I think one day maybe we could do that.
Yes, so that's really the thrust of this article. How about, what's the way to do it? Can you get to that point? And the authors done some nice calculations, which I haven't checked, so I hope these are correct. I should check them, but anyway. If you were trying to get to that solar gravitational lens point, focal point, in 20 years, then you need your spacecraft to travel at about 150 kilometers per second. Which is very hard when you're pointing away from the sun. The Parker Solar Probe, they point out, and we kind of know this because we talked about it, has actually got to nearly 200 kilometers per second. But that's only when it's at what we call perihelion. It's at its closest point to the sun where it's going fastest. And what we're talking about here is something going in the opposite direction, going away from the sun. For it to travel at that sort of speed, you need an extraordinary amount of thrust. I don't think you're talking about chemical rockets to get up to 150 kilometers per second.
Light sails?
So light sails, yeah, that's one of the things that you and I have spoken about before. If you can beam out laser light to a solar sail, a gigantic piece of, something very thin like mylar that's reflective, then the light itself pushes it along and you just keep going so that it just keeps building up speed. There are...
the trouble with that is when you get there, how do you stop it?
Yeah, you don't. You just keep going. That's right.
Yeah. Unless it had something on board to, like, you turn off the light and reverse thrusters or something. I don't know.
Yeah, you're never going to slow it down because even if you turn off the light, it stops it accelerating, but it's still going at that speed. That's right. There's a possibility that, could you do the solar sail trick and basically make it successful? The problem with solar sails is you can only carry objects that are very light in weight or have low mass. And you might remember we've looked at this with, what was it, the Breakthrough Starshot program.
That's it.
Which I think has now ceased. Breakthrough Starshot looked at the feasibility of using a solar sail to send a spacecraft to Proxima Centauri, which is only 4 light years away. And it could be done, but your spacecraft would basically consist of one, what's it called, printed circuit board and a detector. Yeah. There's not really room for anything else. It'd have to be so light in weight, it would be measured in grams rather than kilograms or tons. So that would be the problem with with sending a spacecraft to the solar gravitational lens using a solar sail. So you're talking then about nuclear sources and things of that sort. This very nice article goes into some of the niceties of nuclear thermal propulsion and things of that sort. Even so, it's still a very tough ask to send a spacecraft to that interesting part of the sun's environment where you've got the solar gravity forming a focus. To get there, it's really to get there in 20 years or so. You're talking about really new technologies that we simply don't have at the moment.
Yeah. Well, one day. It might be a long way off, but the time may come, and but then again, we might have figured everything out by then. So, yeah.
Yeah. I mean, the other thing is you'd want to choose. So you've got to choose the direction that you go in.
Yep.
To be in the opposite direction to the planet that you want to observe.
Yep.
The exoplanet. And if you get that wrong, if you choose a planet that's completely boring and has no surface features whatsoever, then you don't really contribute much to our knowledge, particularly our knowledge of whether we're alone or not, whether there's life anywhere else.
It's sort of like leaving the lens cap on the camera when you land on Venus.
Yes, that's right.
Actually, they didn't leave it on; it melted on, I think.
Yeah, well, one of them fell off as well, didn't it? Fall off on top of the scale that was going to give the.
That's right.
There's a ruler that they jettisoned to give the camera something to look at, so you could measure the size of things, and the lens cap landed right on top of it. I think that's what happened.
They've had quite a few Venus disasters over the years, but yeah, you're right. This would be very, very difficult to swallow if you buggered it up, because you couldn't go and fix it. Not like Hubble.
Yeah, well, that's right. You can't move it in any direction. You're stuck on one planet, really.
Indeed. But it's food for thought, though. But one day we'll figure out a way. If you'd like to read about that story, it is at universetoday.com, as Fred said. And we're done. Fred, thank you very much.
Yeah, that was great to talk about all those things, and I hope we'll do it again sometime.
Fun topics, I'm sure we will. If you would like to visit us in the meantime, don't forget to visit our website, spacenutspodcast.com or spacenuts.io, or visit our social media platforms, the official Space Nuts Facebook page or Instagram page or YouTube channel or whatever you like. Or if you want to talk to like-minded Space Nutters, you can do that on the Space Nuts podcast group on Facebook, which is always a lot of fun. Thanks, Fred. We'll see you soon.
Yes, I hope so.
Well, he said that. And thanks to Hugh in the studio, who couldn't be with us today. He was invited by a friend to see a comet. He couldn't wait, so he ran over there. It turned out to be a goldfish. Some people will get that. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.